which is great. Let me make sure I'm actually using the, yeah. Okay, so I did have a couple logistical notes just about, so that's one logistical note, just about the, like, I'm trying to build this database so we'll have everything. Another logistical note is just, I put this on here about when you, I think I even said this in class actually already, it's just like, please assign problems to pages when you do your uploads. Even if it's one page, there's like a step when you upload your PDF where it says, like, gives you the option to assign pages to problems. And a student told me that apparently you can just like exit out and not do it because you've already submitted your PDF. But the problem is that then when the graders get to it, it just comes up as like, this student didn't submit any page, didn't mark any page, didn't like assign pages to problems. And so then they have to start clicking through your problem set to like find the right problems to grade. And it's just anything that's extra clicks is annoying, right? So like anything you can do to help us out makes it easier. Even for like the notes, if you just like assign all pages to problem one, it just saves it one click. You know, it saves the click of like having to click on something and start looking at the pages. And saving any clicks is helpful. Like one reason I hate Blackboard is because it takes 42 clicks to do anything, like mouse clicks. And whereas like this Notion thing I'm using, it's like all keyboard shortcuts and commands, and I can, stuff publishes to the web automatically and updates automatically and stuff. So yeah, okay. So that was that. And then you can look, I mean, stuff, the graders have been good about grading stuff. I think at least problem set 2 has been graded, I think. Problem sets 1 and 2. What did you turn in 3 on Friday? Is that right? Yeah. So I think 1 and 2 at least have been graded. So you can take a look, and if you have any questions about anything from the grading, just come talk to me. Come to office hours. I'm happy to talk through anything. I've even been known to give points back. Huh. Right. But I reserve the right to take more points off if I, no. No, I would rather you come talk to me about what happened. So yeah, let me make sure this isn't broken. I guess this must not be broken because I probably would have heard from students if it was broken. Yeah, so you watch this video. I do want to do a few, yeah, in fact, I'm not, let me just go to the board. I do want to do a few examples, a few more examples of improper integrals, basic ones, and then start talking about the comparisons. One thing we didn't do last time, so more improper integrals. I didn't really have time to do one that carefully that was improper at a finite point. I mean, you watched a video on it, but it's probably not a bad idea just to write out. And actually, I thought it was as an example, maybe something like something that is improper at 2 places, but one of those places is finite. So if you had something like this, if you saw something like this, the integral from -infinity to 4 of 1 over x minus 4 quantity squared. So this is improper at the left endpoint, right? Because infinity is always improper. And it's also improper at 4 because you plug in 4 and you're divided by 0. Yeah. So, right. This is improper at x equals -infinity and x equals 4. And so what's sort of standard to do here is actually break up into 2 separate integrals. And I could pick this middle point to be anything. It doesn't really matter because any other point in between is proper. So I could do -infinity to -10 if I wanted, and then -10 to 4 or something. I mean, I don't know, just because 0 is a convenient number for some people. So you could do something like this, break it up. And then these both, by definition, are limits. And I really do want you to try to write these limits out. Here, I would have b going to minus infinity of the integral from b to 0. And the second one would be the limit, and I can't remember how much I said about this in the videos, but I want to let x approach 4. Right, if I integrate from 0 to 3.999, that's okay, that's proper. Or 0 to 3.9999, as long as I don't actually hit 4. That's a proper integral. So that's why we do the limit from 0 to a. And then I say this, do you guys know this notation? Like, I want to say 4 from the left, approaching 4 from the left. Did I say this in the video? Can't remember if I said it in the video. I think I might have mentioned it, but it was last week, so we've all forgotten. This minus here means from the left, just from values less than 4. It would be a plus if it was values greater than 4. Because we're integrating, you know, because we're integrating from 0 to 4 and 4 is the bad point, then we would be coming from the left, right? Okay, so, and I know it's a little bit tedious to write out all the limits and everything, but this isn't too bad, right? Because we know, I mean, maybe you want to write the indefinite integral at some point, just like the integral of 1 over x, or dx over x minus 4 squared is, it's the negative 2 power, so it's minus 1 over x minus 4, I think. And the minus 4 doesn't, you could do a u substitution, get rid of minus 4 if you want, but it doesn't shift, doesn't change anything. Right. So I think it's minus negative first power, because when you differentiate this, the minus 1 would come down and cancel and give you the minus 2 power. Okay, I think that's right. So then if you're going to keep going with this, you would, I'm sort of doing 2 integrals. I mean, and sometimes what I do is I'll break things up. Like what if we called this, sometimes like I'll call different ones I, like what if this is I1 and this one's I2? Just so that you don't have to like keep rewriting everything all the time. Or you could even make I could actually make, let me even do this. If I'm lazy and don't want to write the limits, let me just make this I, oops, wrong color. Let me make this I1. You just had, so there's some accounting problem. You don't want to have like careful accounting when you're writing down solutions so that you know what you're doing is going to make sense and you're plugging things back in. And just because it's a little bit annoying to write the, let me call this I2. Actually, I don't know why I did that. It's not that big a deal. Probably would have been fine. So let me just say this. So I1 is negative 1 over x minus 4 from b to 0. Also, my b's really do look like 6s a lot of times. So we'll try not to pick the number 6 anytime I'm going to use. Okay, so, and again, you know, you can just be as pedantic about this as you want. Write this down as carefully as you want. Minus 1 over 0 minus 4 minus 1 over b minus 4. So that's 1/4 plus 1 over b minus 4. Right? And then if we take the limit as b goes to negative infinity of I1, that's the limit. It goes to negative infinity of 1/4 plus 1 over b minus 4. What happens to the bottom here? As b goes to negative infinity, this is a big negative. Right? So 1 over it is what kind of number? 1 over a big negative is a small negative, right? And so that's, as b goes to negative infinity, that's going to get smaller and smaller and just go away. Sometimes it's nice to track whether it's a positive or negative. So this is literally just 1/4, or 1/4 plus 0, which is 1/4. Any questions about anything I did so far? Questions are good. Maybe I made things more confusing by just calling these things different things and pulling them out. I don't know. Yeah. No.
We just did like the integral of the
Yeah, that's just, I guess I skipped some steps of rewriting this as x minus 4 to the -2 power. And then use the power rule, adding 1 to the power. So yeah, and then I changed this back. And I guess since I've done this a cajillion times, I guess I just got used to in my head to knowing that this is -1 over x squared. The derivative of 1 over x is -1 over x squared. So the integral of 1 over x squared is -1 over x. Those are just like in duality to each other. And the -4 is just a shift. So even if you did a U substitution, it wouldn't change anything. Okay, good. So that's the first part. So this part converges. This converges by what we just said. The second part, I2 was this thing, right? So that's -1 over x minus 4. Now from 0 to a, doing that right? No, wait, what? Yeah, maybe. Oh, there's 3 negative signs here, aren't there? Did I do the right number of negative signs there? Okay, this is still -1/4, right? Okay, so that's -1, or it's -1 over a minus 4 minus 1/4. So the limit as a goes to 4 from the left of this expression is the limit. And here's where things get interesting. Okay, I guess it's officially this limit right to this. No, there's no a. Okay, now this gets interesting, right? Because now if I plug in a number that's just a tiny bit less than 4, what happens to a minus 4? What's it really close to? 0, right? If this is like 3.999 minus 4, then that's small. So I can do the same kind of things here where this is a small negative number. And so actually, -1 over a small negative is what? Big positive. Big pause. Okay, and so that's going to go to plus infinity actually. And the -1/4 doesn't matter. So that's plus infinity. So that means the second piece of our integral actually diverges, right? This guy actually diverges. And we say that if any piece of an integral diverges, the whole thing diverges. Even though the piece from -infinity to 0 was finite, we still don't want to call we definitely don't want to call an integral, the whole thing convergent, because that would suggest that it equals some number. So that's also the thing. If any piece, right, if any piece of an integral diverges, then the whole thing diverges. Okay. So that example up there diverges. Integral from negative infinity to 4, 1 over x minus 4 quantity squared. The x diverges. Okay. Any questions about anything? I claimed last week that there was going to be a controversial example. And I never actually got to it. I think I said something about it at the very end of class last time. But let's actually talk about this example. So this is the integral from negative infinity to infinity of x over x squared plus 1. Which, if we drop the bounds, this is not the worst integral. Indefinite integral, meaning find antiderivative. It's not the worst. It's not the hardest one in the world. The bottom has an x squared in it. So if you let u be the whole bottom, then the top will have an x in it. So that's a good choice of a substitution. It's often nice, like look for the thing that's buried under like a square root or in the denominator and see if you make u that whole thing, if it helps. That's like a great strategy. So if we do u as x squared plus 1, du is 2x dx. By the way, I could put the dx up here at the top also, it doesn't matter. It's kind of like a little multiplied dx. So sometimes you see integrals written this way, which is fine, doesn't change anything. And so x dx is actually 1/2 du, right? I move the 2 down over here. X dx is 1/2 du. And so I can plug that in. And so this thing is, what is this? 1/2 du over u. Doing that right? That's okay. And so the 1/2 can come out. So this is 1/2 natural log. It's actually officially absolute value of u, which I do want to say because we're going to have negative values here. And so that's 1/2 ln. Actually, it doesn't really matter because the x squared plus 1 is always positive. It doesn't really matter whether I put the absolute value there or not. Okay, so that is that, right? That's the indefinite integral. But if I want to do it like as a definite integral, although improper, I want to give two approaches. And this is the thing that I kind of came up last Wednesday. We didn't really get time to get into. What if we write, let me just copy this. What if we just write the limit as b goes to infinity of negative b to b? That seems okay, right? Right, I'm just like, they're both endpoints go to infinity, so just like use the same letter and let them both go to infinity. Well, what do we get in this case? Well, we just saw that we get 1/2 ln x squared plus 1 from negative b to b. Can't draw b. So what's going to happen when I plug in the b and the negative b? They'll be the same, right? Because we're squaring both. So I just want to be super, write it out. It's ln of b squared plus 1 minus 1/2 ln of negative b quantity squared, which is b squared plus 1. So that is 0, right? So it looks like this has the integral is 0. And I think actually, if you look at the graph, I think again, I was trying to shoehorn this in at the very end of class last time and not doing a great job of it. If you look at the graph, you might actually believe this. X over x squared plus 1. Do you believe the area is 0? There's some positive area here and some negative area here, and they cancel out. Yeah. Maybe. I'm gonna say what?
Don't dare say yes, because I feel like that's the only answer.
I'm not predictable, huh? Okay, so let me give the second approach. So that says that the answer is 0. Yeah. Okay, so, but approach number 2 is what if we actually do it as 2 separate, like I said in this example I'm erasing right now, it's actually improper at 2 points. And so maybe we should break it up and actually do 2 separate improper integrals, right? So approach number 2 is let's rewrite this as the integral from -∞ to 0 plus the integral from 0 to infinity. Again, 0 is arbitrary. You could have chosen 5 if we wanted to. And so, okay, now let me be pedantic. If we, again, just turn this into a limit, right? And now I'm gonna use a different letter. C goes to infinity. The integral from 0 to c. Right? And now we can sort of use the same idea we used up here, that it's the integral, these are zeros. So this is the limit as b goes to -∞ of 1/2 ln x squared plus 1 from b to 0. Zero to c. Too many parentheses or something there. Okay, now what happens when we plug in? Here we get when we plug in 0, we get natural log of 1, which is 0, right? So I'm just going to skip that step and just write -1/2 ln negative b squared plus 1, right? Plus the limit. This is 1/2 ln c squared plus 1. And then -0 for the same reason, like ln of 1 is 0. And now, go ahead. Please. because when I plug in 0 and then minus, what do I get when I plug in b? I think there's a minus sign. It's like 0 minus this. Okay, the question then is, what are these two limits? What is the limit? What is this limit? What happens to ln of c squared plus 1 as c gets larger and larger? If this is big, then this inside here is big. And ln of big, what was ln of big? Big, maybe less big, but big. I think I wrote it as like capital B, but lowercase ig. Signify less big, but this still gets bigger and bigger without bound, and this goes to infinity. So this is actually, this limit right here is plus infinity. And this limit right here, it's the same idea, right? It's minus infinity. So the answer is really minus infinity plus infinity. Is that 0? Yeah, maybe. I don't know, maybe it should always be 0. So you're shaking your head. Why can't it just be 0? I need to put you on the spot. But yeah, I could certainly show you examples. Like, what about the limit as x goes to infinity of x squared minus x? That is infinity minus infinity. But x squared goes faster than x, so that's not 0, that limit's also infinity. I think also the principle I wrote up there, if any piece of an integral diverges, then the whole thing diverges. So in fact, this part of the integral diverges. So we kind of have to say the whole thing diverges. It just seems weird to people. I actually have some more compelling ways to look at this, but you need we're going to do a lab later. But it's sort of like, actually though, exactly what I said, like if these are two separate numbers, they can go to infinity at different rates. And I actually claim that I could make this equal to any number you want. I can make this equal to like 47 by letting this go to infinity at a slightly faster rate than this. It seems implausible, but it's true. So actually we have this lab we're gonna do later, maybe pretty soon, where you can actually see this happening. And it's kind of neat. Actually, it's not that hard to see. If I put some relationship between B and C, like in the approach number 1, B and C were basically the same thing. I mean, I guess they're opposites here. But B and C were basically the same thing. If you make them not the same thing, then you can get different answers. And that's why infinity minus infinity is considered an indeterminate form. Considered an indeterminate form is what it's called. Which I'm kind of fond of these, and at some point we'll talk about them more carefully. And you may have seen it, the word before, but other examples, 0 over 0, infinity over infinity, 0 times infinity, 0 to the 0th power. 0 to any power is supposed to be 0. Anything to the 0th power is supposed to be 1. I think there's other ones like infinity, and there's other ones, etc. But it could equal anything depending on the context. So what we say actually is that So we just go back to that principle up there, which is that really, since a piece of this diverges, we say the whole thing diverges. Go back to the principle above. Some piece of the integral diverges, so the whole thing diverges. And even looking at this picture, like the area is only 0 if you cut it off at the same place each time, right? If I cut it off slightly more, you know, if I did it like this, I'd get some positive area. If I did it like this, I get some negative area. And if you let those grow at different rates, you could get different, you can get different answers. So the whole thing diverges. And so that's actually the answer that we would say for this integral. And that's why it's good to break up the integrals into different pieces. So I'm actually gonna say like this first answer is not right. Okay, that's not the answer that we want. We just want 0. We just want that it diverges. Yeah. The principle or the? Don't. I'm saying it's very plausible. It's a plausible thing to do. And it's what students seem to want to do. And if I gave you this problem on a homework without talking about it, you might have done that. But it turns out, and it's somewhat of a philosophical question, you know, but mathematically it does make more sense to just say this whole thing diverges, because certainly the integral from 0 to infinity diverges, and so it contains infinite. Anything that contains pieces that are infinite, we're just going to say are infinite, unless it's very specific. Yeah. Oh, right here? Like, why did we pick 0?
No.
Sorry. Oh, like, is there a function I could put here where this would be a valid answer?
For example, in the functions of
Oh. Oh, what's the step? Like you see those proofs that like 2 equals 1 by somehow it like, have you seen those like where it's like somehow they secretly divided by 0 at some point and they sort of obfuscated it? So you're saying there's something, is there something similar here? Well, it's a little more abstract. I guess I would say the problem here is just going from this to this and saying that this is putting a restriction on here that's sort of arbitrary, that these two b's have to go to infinity at the same rate. That's the, like I could have put b in like 7b here if I wanted to. Nothing would have been wrong with that. And I think you would get a different answer if you did that. So I think that's kind of, if that's what you're asking. Yeah, it's kind of silly, but yeah. No, it's a good question. Like, if I tricked you, then how did I, or I tricked myself, how did I do that? Okay. Oh, please.
Yeah, because we got the indeterminate form, would it make sense for us to go and bring in these like filters?
Yeah, right. Sometimes you can resolve indeterminate forms in certain situations. But I guess the point here is that like, there's like, even making, I guess it's at the point of even making this step is doing something before you would even think about resolving an indeterminate. It's actually doing something kind of wrong, which is saying that like, this is not really equal to this, because I really can't say that these two endpoints are going to infinity at the same rate. So we will see later, like we'll probably do, if you haven't heard of L'Hopital's rule, I'd like to go over it at some point, but you can resolve indeterminacies often with L'Hopital's rule. But here it's like, before you even get to that, like I could make this, depending on, I mean, for this choice of letting these two endpoints go to infinity at the same rate, the answer is 0. But I made a choice that I can't really make. And so when you have an indeterminate form, there's usually some underlying choices that are like some expressions that you have that you can resolve. Here, I'm saying it's even worse because I could change these and make the answer be anything I wanted, even using L'Hopital's rule or other kind of things like that. So yeah, it might have sounded a little abstract, but okay. Other questions? I don't know. I like to get into this a little bit, this philosophical discussion. So it's already been 40 minutes. So let's take a break for a few minutes and then come back and think about the video that you watched for today. And if you have questions about it, I mean, I'll do some more examples, but if you have questions specifically about that video, please be ready to ask them. All right, take a 5-minute break. You can stand, you can walk around. Oh, can you?
I cannot do it right now.
Oh, it's closed. Can you email it to me?
I can.
And just tell me that I said it was okay.
Thank you.
This graph's on the screen. Just to think about, I told you the p-test, there's the p-test from 1 to infinity. There's also a different p-test from 0 to 1 where it kind of everything flips. And remember, like, when we went from 1 to infinity, well, you can't see it here because 1's over here, but the red graph dipped below the blue graph and dived down towards the x-axis, and it choked off less area. That's why it was finite. Remember, I showed you those pictures. Or why, like, it's not unreasonable that it's finite. If anything is going to be finite. And you can sort of see between 0 and 1 here how everything flips, because now, like, 1 over x squared is a lot bigger than 1 over x, because x is close to 0. I mean, that's the thing that's hard to wrap your mind around. But right, when you square, I mean, this is actually going to come up later in an example we're going to do, but if you square a number less than 1, it gets smaller, right? Versus if you square a number bigger than 1, it gets bigger. So if you square a number like close to 0, it gets actually much closer to 0. And then you do 1 over it and it gets big. So this graph has a lot, this red graph has a lot more area under it than the blue graph does, between 0 and 1. And that's actually why this ends up diverging. Actually, both of these end up diverging, but if you go to like 1 over root x, it's even less. I mean, I could graph that in there and it'd be even less area. And that's where you start to get the finite area. But it's sort of fascinating how this stuff switches. Stuff flips as you go between 0 and 1 versus 1 to infinity. So it's worth thinking about that sometimes. All right, but I just wanted to make a comment about that. And it'll come up, like I said, it'll come up later. Do I have this position right? I'm gonna have this too high. Sorry. I don't know what I was doing. Go up. Okay, close enough. So, all right, how was that video? Comparisons of improper integrals. Great, we're done. Let's go home. No, so, all right. Did anybody have questions or something struck you as weird, or you'd like to go through it something more carefully, or should I just do more examples or more examples? I will say a little bit, maybe in general, that, you know, there's this informal approach and this formal approach, and I do want you to be able to do the more formal approach. But you should be able to look at an integral and pretty quickly tell from the informal approach whether you expect it to diverge or converge. So if I give you something like the integral of from, let's just say 10 to infinity of x to the 5th minus x cubed plus 73x squared plus 1 over x to the 6th plus 31 x to the 5th minus x to the 4th plus x cubed minus x squared plus x plus 1. If I ask you to integrate that and give me an answer, you should be very unhappy. Well, okay. I mean, it's, if it converges and it has an answer, it would be extremely hard to integrate this. But what did I sort of say in the video you should think about? Like, I claim this sort of, you can think of this in a more simple way. Yeah. Yeah, in behavior and maybe like dominating behavior, like what dominates? The powers, yeah, like the powers. So like, as x gets large, because this really is the limit as x goes to infinity of, or not x, b goes to infinity of 10 to b. As the inputs get large, what dominates? X to the, on the, oh yeah, on the bottom it's x to the 6th, and on the top it's x to the 5th, right? So the end behavior, right, is that this whole thing will go to 0 because the bottom's larger degree than the top. So it has a chance to converge. If this was like x to the 7th up here, you'd immediately tell me it diverges because this expression doesn't even go to infinity. It doesn't even go to 0, sorry. But you're right, it goes to 0, but if you just look at the biggest terms on the top and bottom, the point I was trying to make is that like, as x gets large, these get much smaller in comparison. And as a certainly as a percentage of the entire value on the top and the entire value on the bottom, they start to contribute less and less. Right, because if x is like 10 to the 10th power, then this is 10 to the 50th, that's 10 to the 30th. And even though those are both unimaginably huge numbers, 10 to the 30th is a tiny percentage of 10 to the 50th. That makes sense. So the informal approach is that this is basically like the integral from 10 to infinity of x to the 5th over x to the 6th, which is the integral of 10 to infinity of 1 over x, because of cancellation, right, which diverges. Because we know this is natural log, and natural log goes off to infinity, or you can remember the p-test, however you want to think about this. And so in my mind, even though that's a horrible integral, I think I immediately know it's going to diverge. I put 10 here because I was worried about the bottom being 0. And I thought, if I put 10 here, these two numbers get pretty big compared to the rest, so I'm probably okay. Sometimes I do that just to avoid the bottom being 0 because I don't like it's, I could have accidentally put a second improper point at some finite point that I didn't intend to. So, but does that make sense? You just sort of like cover up. I mean, it's, you know, it's sort of nice. You just think this does behave like 1 over x as x gets large. Is that fair? And so you get immediately. And in fact, I probably wouldn't ask you to do something like this, the formal approach, because it would be sort of unpleasant. But I guess if we call this, maybe I don't want to write this again, but let's call this like f of x. I guess the more formal approach would be that, and I mean, again, it's sort of like you'd have to believe it or not believe it. More formally, I bet this function is less than, 10 to the 10th times 1 over x, and greater than or equal to 1 over 10 to the 10th times 1 over x. Remember that thing I said about sandwiching the function between two, using constants to sandwich it? And I'm picking just a ridiculously huge constant here. because for small values, this may not be true, like, but for large enough x, and probably 10 is large enough. Like there's a huge discrepancy between these two functions, right? But they all go to 0 as x gets larger and larger. Like here I have the 10 to the 10th on the bottom. And there I have the 10 to the 10th on top. Or I can make it 10 to the 1000th if I really wanted, you know. You can make it as big as you want. It's just a multiplied constant. And if you graphed all three, I'm not going to bother typing this in, but if I graphed these three, and I could probably make the constants work so that at some point this is between some sort of big multiple of 1 over x and some small multiple of 1 over x. Right? I think it was believable in the video, the examples I showed you. So maybe this is less obviously believable because it's so complicated. But there is something here. So then if you integrate all three of these from 10 to b, say, I can pull the 1 over 10 to the 10th out of here. I can do the integral from 10 to b of f of x, which is that integral we had up there. And I can do the integral 10 to the 10th times the integral from 10 to b of 1 over x dx. And as we take the limit as b goes to infinity, making these improper, we know this diverges, right? 1 over x diverges. So this goes to infinity. This diverges. And that's where this constant doesn't matter, right? Even though there's a 1 over 10 to the 10th here, which seems tiny, if this is getting arbitrarily big, it doesn't matter that you have 1 over 10 to the 10th in front. It's still going to get bigger and bigger and bigger. And so this is trapped in between. I mean, I guess what I want to say is like this goes to plus infinity, this goes to plus infinity, and this is trapped in between. And if you trapped in between two things going to plus infinity, I always try to picture things in my head of like two blocks rolling along on some thing, and I'm like trapped between them and I can't get out, and like they're both going to infinity, and I'm just like, shit, bye guys. I guess I'm going this way forever. So yeah, that's kind of how I picture it, right? These are both going to infinity, so this must go to infinity. I mean, this isn't that much more formal than what I wrote. I just think it's at least a little more mathy to say like, there's some constants we can pick to put this function between to make that work. And certainly for smaller values, I mean, for less complicated functions, you could actually graph them all and sort of figure out the constants that would work and demonstrate it on a picture, you know, like a graph that would work, right? Yes. Yeah. Yeah, well, I mean, those are about two things where these are actually going to the same value in the limit, and so this has to go to that. So like if these were both going to 4, then this would have to go to 4 also, right? Actually, I made some caveats about like, you have less than, but when you take the limit, it might become less than or equal to. I was actually thinking about the squeeze theorem there, because you have two things that are different, but they both end up going to 0 or something as the limit goes to as in the limit. And so they actually, even though one thing's bigger than the other, they land up at the same place. So yeah. But it feels philosophically like the squeeze theorem. Good. Okay, so I told you this whole thing, like, watch the powers. Let me give you another example. Let you guys think about it. So I'm gonna actually have you guys think about it just at your seats, like talking to your neighbors and stuff for a little bit. And try to figure out what's going on. So here's the example. The integral from 0 to 1 of 1 over x squared plus root x. This is improper at 0, right? So turn to one side and say hi, introduce yourself to someone. And then start thinking about this problem together. That's what new friends do. It's a good way to bond. You can't integrate this directly. You have to do some sort of comparison with something. And the question is, what do you compare to? Did you write this? Come on, Akman. Did he write this? Maybe I should have written this here. That might help. This analysis was as x got bigger and bigger, getting larger and larger. Yes. Sorry.
If there's any like particular like methods of picking constants like for the comparison.
Well, I mean, first you have to figure out which function you're comparing to. Like, are you comparing to x squared, say there on the bottom? And then you might want to like graph, like, you know, like in the video, I think I showed it where like I had like x squared minus 1, and I actually graphed some of the constant times them to see what would work. And so it's the same idea. I think you might actually want to like graph stuff or think about stuff. And whether x squared is even the right thing to compare it to is a question. But you also have to think about the fact that you're really close to 0 now instead of getting bigger and bigger. So they're all very important things.
Okay.
What are you guys talking about?
Not sure. You have an idea.
Yeah, I think, yeah, x squared is smaller than x squared plus root x.
Oh,
There's 1, right? And we need another function here.
and that's bigger.
Yeah, that's very true. So we're not trying to compute this integral, we're just trying to ask whether it converges or diverges, right? So that's the real question here.
Yes. 4999.
What are you guys thinking? What's a 50-50 chance? Oh, converge or diverge? Great. I'm really doing a great job teaching here. Bang up job. This isn't probability.
Still math.
Breaking up.
Oh, but I just asked 0 to 1. So you don't really have to, it's only improper at 0, right? There's no infinity in this integral, right? It's just, but I can't plug in, it's improper at 0, right? I can't plug in 0. Nice, geniuses. Oh.
I don't know where we did integration.
Wait, you actually integrated? But the x plus root x is on the x squared plus root x is on the bottom. But you can't just integrate the bottom. It's 1 over something. I'm definitely stumping everyone. I'm seeing so many incredibly wrong ways of thinking. I'm very proud of you guys. You cannot just integrate the bottom. The answer is not 1 over x cubed plus 3/2 x to 2/3 x to the 3/2.
Definitely bigger, right? Then this diverges, right? 1 over x to the power of 1 over 800 diverges from 0.
Hey.
Say it diverges, like that denominator goes faster than the numerator.
Well, that happens in our other examples that we've seen. Like maybe I should write on the board some things we know. We know the integral from 0 to 1 of 1 over x squared. We know this diverges. Right, you remember that? Because we got the minus 1 over x when we integrate this, and we're trying to plug in 0, so we're plugging 0 on the bottom. So that blows up. And we also know that the integral of 1 over root x dx converges. Because if you try it, and I think this is what I did in the video. I think I did these examples in the video, right? Or at least one of these examples in the video. The previous video about when the function blows up. Right, if you just try this, you end up getting an x to the 1/2 when you integrate. And now you can plug in 0 and it's okay. It's really a matter of whether the x ends up on the bottom or not after integration, right? If the x ends up on the bottom here after integration, you're trying to plug 0 into something on the bottom and it's gonna blow up. Yeah, I think so, but the question is which P?
But I thought that if P was.
That's for 1 to infinity. This is from 0 to 1. We said from 0 to 1 it flips, right? I mean, I think I said this, but
No, so for that, for P.
yeah, for this integral, remember it flips exactly what happens. And you should try, I mean, again, if you haven't written these two integrals out, you should try to write them out and you'll see it really concretely, that this one will diverge because you end up with a 1 over x in your antiderivative and you're trying to plug 0 into it. 1 over 0 is bad. When you integrate this, you end up with an x to the positive 1/2 in your antiderivative, right? Because you add 1 to the, this is x to the minus 1/2 power. When you anti-differentiate, you end up with you add 1 to the power, so you end up with an x to the 1/2. But now plugging 0 into x to the 1/2 is fine. That's just square root of x, square root of 0. And so here, this one, actually, it flips from the 1 to infinity situation where this diverges for p greater than or equal to 1, and it converges for p less than 1. Right, I think I wrote this on the board last class, but it's weird, and I think I wrote it quickly without doing it. But you should do these examples out. I mean, I think you may have had to for the video. But the thing that's so challenging about this is what do I compare it to? It feels like p equals 2, right? 2 is the bigger power. This is where the informal thing may hurt you. And I saw this group over here trying to stick this between two functions, right? Because if you can stick this between two functions, then you can start doing one of these comparisons, building in comparisons with inequalities, right? So let's think about this. X squared plus root x. Let's try to compare it to x squared. Like this is bigger than x squared, right? Is it less than or equal to 2x squared? Guess I should put question mark here. When x is close to 0, this is what's interesting. This is for, this is for x close to 0, right, and positive. That's what we care about here. We're integrating from 0 to 1, but 0 is the bad point. We can't plug in 0 here. We get 1 over 0. So I actually plotted all three of these on the screen. So the blue graph is x squared. The yellow graph is 2x squared. Can I zoom in is the question. Yeah, look what happens close to 0. Right? Why are you saying, Ahmed, why are you saying that? Is bigger than that. Yeah, like right when x, like if x is 1 over a million, 1 millionth, then what is x squared? It's 1 over a millionth squared. It's 1 over a million squared, which is 1 over a trillion, I think. But what's root x? 1 over 10 cubed, right? You're just gonna have the power. So actually, this is much bigger. So root x is much bigger than x squared when x is close to 0. So in fact, yeah, this is not true. So it's actually kind of, it's a weird thing. I wanted to do this because it makes the point, like when x gets large, the bigger power dominates. But when x gets small, the smaller power actually dominates, and it's very weird to think about. But like root x is much bigger than x squared here. So this is not true. But we could put root x here instead. That's actually the dominant function. And certainly we can do that, right? Adding x squared is adding something positive. And I claim that this is probably true also for x small enough. So what if I graph those instead? Because notice here the red graph is on top of both the yellow and blue graphs. Like I was trying to, the lesson you're here was, I was trying to claim red was less than yellow on the screen. And that's not true, but I do claim that this inequality will work. So let's try it. This is where like thinking about the actual numbers and plugging in small values and plugging in large values is actually really helpful. I know it's somehow not natural, which says something about your education, I think, but just trying stuff. So what was I trying to claim? That the red is less than the yellow. Yeah, the red is less than the yellow if the red gets close, if the x's get close enough to 0, right? So you can see it. Well, it's hard to see, but you can see the red. It's really close to the. It's really close to this one. It's close to root x because x squared gets so small when x is small. So that's why it's hugging against. That's why the red is hugging against the blue. But then it's definitely less than the yellow, right? And so it's a funny thing, like that's, it's just a funny principle that like when x is small, the smaller power actually dominates, which is just hard to think about, but it makes sense of any of these examples, you know, or even just like one, I mean, an easier example maybe this is even too hard to, like too abstract. You get 1/16 versus root x is 1/2, right? So like the root x is actually bigger. So root x is actually the dominant term. Okay, so once we have this established, then we can finish off the problem having this kind of inequality here. And we can say, I can now do things like flip over the inequalities, right? And then integrate both sides and then take the limit, you know. Let me just do that the formal way we do it just to see what happens. It's probably worth writing down and we still have a couple minutes left. So that's 1 o'clock. So here what happens is if you flip this over, you flip all the inequalities, right? Right, the inequalities flip that way. And maybe just to put them back the way we like them, maybe I'll just rewrite. So they're gonna just, it's just nice increasing order, and then you integrate both sides. But I really want to go from, you know, a to 1 over root x. You know, some a is small, positive, because we can't plug in 0, so we don't want to be improper yet. So that's less than integral from a to 1 of, you know, at some point this becomes kind of rote. You're just gonna flip over, switch inequalities. Once you establish something like this, you're gonna be done. You just have to follow these steps, and then you're gonna be done, and you're gonna see what happens. And then we take the limit as a goes to 0. I guess from the right. And we get 1/2 the integral from 0 to 1. And you could compute this if you wanted to. You know, if you're not sure what's going to happen here, if you don't want to just trust the p-test, which you shouldn't, just trust the p-test. This is not that hard to work out. And then take the limit as a goes to 0. And you'll see you get a finite value. And this becomes the integral from 0 to 1 And this becomes the integral from 0 to 1. And in fact, this has some nice value, like 2 or something. I think I did it in the video. I can't remember now off the top of my head, but I think it has the value 2. So this is a number. This converges. And actually now this really is like a squeeze. Well, no, it's not quite because this is 1. So it's not squeezed. I almost got squeezed, but this converges to like 2 or something, I think. So half of it will converge to 1. And I don't know what this converges to because I don't know how to integrate this function. I don't think anybody does. But it has some numerical value. It converges. Because it's trapped between 2 things that converge. Does that make sense? So when you're going to infinity, it's easier because you just compare to the biggest power. But when you're going to 0, it's, I mean, honestly, this has come up like I put this question on like a problem set years ago. And in my head, I was thinking of just the like I was just thinking, oh, it's going to behave like 1 over x squared. So I messed it up. So like, this is not an easy question, but it's interesting. It shows you how much you have to think carefully about what the x values really are. Are they getting big? Are they billions, billions? Are they getting smaller? Are they 0.00001? You kind of have to play on the real number line. And actually, you have to be there. Put yourself on the number line, damn it. It's there. Okay, anyways. All right, so hopefully that made some sense. If not, you can always come talk to me. So, all right, have a good Monday. I think there's assignments for Wednesday or Tuesday night. Oh, I think I need to post the videos actually for Tuesday night, sorry. And that's it, we'll call it a day.